Okay, good morning, everyone. So let's start today's lecture. So far, second, there is a message. Yes, I'm assuming this is the official Python, PyTorch icon, but I have to double check. So, um, so far in the course, what we have done is we have created all the theoretical building blocks of any primarily supervised machine learning algorithm. Um, we have looked at how to look at data in terms of something, learning something from it. We have seen how to construct the hypothesis function, which is basically your network, output of your network. We have seen how to construct a loss function out of it. And we have seen how to optimize that loss function with respect to the unknown weights. Okay? These are all the components of any supervised machine learning algorithm. Now, from in the last three lectures, we would primarily be looking at high-level practical implementation of it, the way we actually implement it. Okay, usually when you implement machine learning algorithms, you don't need to work very hard. You don't need to calculate the backtracking. You don't need to do the back propagation through the network. You don't need to write the optimizer for it, like stochastic gradient descent. All these things are taken care of very well by packages like PyTorch. Okay, so the last three lectures, we would look at these practical aspects, how to actually practically implement it. And you would see that anyone who even might not have very good knowledge of machine learning can use these packages. It's good to have the knowledge, particularly if you are a researcher in the field, because if you want to, let's say, modify these packages in some way or modify the algorithm in some way, it's much more easier if you understand what it actually is doing rather than doing a random search, which a non-practitioner of the field will do. Okay, so let's start first with a review of what we have done so far, primarily focusing on neural network. Okay, so what we did yesterday was we studied neural networks. And what we saw was that we can write the neural networks, by the way, are universal function approximators. They can approximate any function given enough complexity and enough computational resources and data. So let's say we had data x and y, and this is some complex function f of x equal to y, and we want to learn it. What we can do is we can say, okay, let's construct a neural network for it. Let's do something like this. Pass it through sigmoid, pass it through second layer, pass it through sigmoid, and maybe we can repeat it for a few layers, and we call this y hat. Okay, and then we try to minimize the loss between y and y hat. Okay, we want to minimize some norm of this if it is like a regression type of problem, or we look at some probability-based norm like binary cross entropy between y and y hat if it's a classification type of problem. This much, I think, should be clear for everyone. I'll stop here for a second and allow you guys time to ask questions about what we have studied so far, because as I understand, some of you have questions. Nick, you had some questions. Do you want to ask them now?
Okay, am I audible now?
Yes, you're audible.
Yeah, basically, I have three questions about the previous course in terms of linear regression. Basically, you have taught us there are three bases that we can use. Number one is a polynomial basis. Number two is Gaussian function, and the third is Gaussian distribution.
Yes.
The first thing I want to make sure is that in the previous course, you given us the formula of Gaussian distribution, and in the formula, basically the basis train equals np dot exponential and minus x minus centers and powered by 2, and then divide 2 minus sigma powered by 2.
Yeah.
Is that correct? But in the code, what I saw in the previous video is it was 2 times sigma, then times 2 instead of sigma squared, sigma powered by 2. So I want to make sure which formula is correct.
So I'm assuming I would have to double check, but I think a Gaussian distribution is something like this. This is the definition of a Gaussian distribution.
Oh, okay.
You can drop these things because these are just scalars. So basically this thing is what matters. Generally for us in our implementation, this is also a constant because we are not changing it. So you can, roughly speaking, for writing the basis, you can just write this x minus mu whole square divided by some constant. So that would work.
Oh, okay, I see.
But the
So this,
Gaussian probability distribution is this. I will double check it for you, but I'm like 90% sure that it's this.
uh, could I set a photo to the chat box, because that photo will have the code you taught us in the previous video. But which is fine. I just want to make sure which mathematical formula for Gaussian distribution is correct. My second question in terms of Gaussian distribution is that in the previous code, you set the value of sigma, which equals weather's factor times centers 1 minus centers 0.
Yeah.
So what I want to know is it necessary for the value of sigma, which must have relation with the centers or not?
It's not necessary, but it's advisable. So let me tell you why. So basically what you're doing is in the Gaussian basis regression problem, what we are doing is we are saying that, okay, this is our interval. This is the range of x's that we have. And we
Yes.
divide it, let's say in certain number of bases, right? Then we say that each of these points contain the center of a Gaussian distribution. Okay.
Yes.
And what I
Yes.
did, I think roughly what I did is I said that the standard deviation is 2 times this, weight factor times this. And I think weight factor was probably 2 in my case, right?
Yes. Yeah.
So why is this advisable? This is advisable because if you do that, roughly you would see that your Gaussian distribution would cover the entire X, right? If, for example, I take too small a sigma, then you might have a Gaussian base like this. And then this is not nice, right? Because
Yeah.
you don't have anything to cover this region with, right? If on the other hand, if I take too large a sigma, then your Gaussian base would look like this. Then there is no difference between this base and this base at this location. So the two bases are exactly the same. And you would have a problem when you do A transpose A inverse, because if two bases are exactly the same, it means that they would look like two same columns in your A matrix. And if they are the same column, then you would not be able to find the inverse of A transpose A. So that's why it's good to relate it to the step size, so that you don't run into these issues. But it's not compulsory. You can have, for example, here you can have a 2 times step size. Here you can have 0.5 times step size. It's fine. You can do that. But generally, it's advisable to keep it constant and related to the step size.
Okay. Thank you. Yeah, it makes sense. So the final question about the linear regression model is about, I think you also taught us about regularization, right? In
Yeah.
terms of loss regression model and also range regression model. So what I wanted to confirm is that is the only difference between linear regression and the range regression is that the range regression and the extra part of the cost function, which is W transpose W. And
Yes.
is that the only difference?
That's the only difference.
And also the only difference between loss regression model and the linear regression model is that loss regression model put an extra part, which is the absolute value of Wi at the end of the cost function.
Yes, that's exactly true. So basically, so linear regression, the loss is y minus AW transpose y minus AW. This is linear regression. If I
Yes.
add plus lambda time W transpose W, this becomes ridge regression. Okay. And if I, let's say, remove this and add this, W absolute or W1 norm, then this becomes a lasso regression.
Yeah, okay. Yeah, it makes sense. Thank you, Professor.
Is that it?
Could I? Yeah, I just have one one very final question
Go ahead.
about your Taylor series approximation. So what I wanted to ask uh, I think you mentioned a couple of times about the disadvantage of polynomial basis in terms of Taylor series approximation. So what I want to know is, in some cases, if some of the weights value is equals 0,
Mhm.
and the matrix A transpose A might not be easy to calculate the inverse of the A transpose A because it might have some lies in A transpose A which are linearly non-independent.
Yeah, exactly.
So is that one of the disadvantages you mentioned?
That's the main disadvantage. So because remember, we are doing this, we are finding these bases on the range of x, right? We select some x, which is dependent on the data, and then we create these bases on that x, right? So my
Yes.
basis, polynomial bases are x power 0, x power 1, x power 2, and so on, x power m, right? Now,
Yes.
if the range of x's, in some cases, you might have some relation, some linear relation between the polynomial bases. In that case, the inverse of A transpose A becomes difficult to calculate. On the other hand, if you have something like DCT bases, you would never have this case because DCT, all bases are linearly independent of each other. So you would never have the case where you cannot find A transpose A inverse. Okay. In fact, A
Uh,
transpose A inverse is just 1 by M for it, 1 by some weight. Um, so it's very easy to calculate and it's almost always calculatable. So that's a disadvantage of polynomial basis, but there might be certain cases where polynomial bases are better, work better than DCT bases. I don't have any example from the top of my head, but the main disadvantage is that the bases are not linearly independent of each other in all cases.
yeah. Okay, thank you, Professor. Yeah. So now I memorize this more deeply. Okay,
Okay.
thank you.
Any other questions for anyone? Please feel free to ask. It was actually fun listening to all these questions from Nick. Anyone else wants to ask any questions, please go ahead. Don't be shy. It actually helps everyone understand. Okay. Yes. Should the parameter u must help to shift the Gaussian basis, cover the span of data in X's? Yes. So basically, what we do is we find this mu. Let's take a new page. So how do we calculate this mu? What we do is we say that okay, let's take the range of x's that you have. You find x min and x max, the value, the minimum and maximum value of x in your data, and you say the range is x max minus x min. And then you say that okay, let's select a number of bases that we want to choose. Let's say we want to choose number of bases equal to 5, then we say that mu, or let's not call it mu, let's call it delta mu. Delta mu would be r divided by number of bases. Okay, so basically what we do is we take this range and we equally divide it into parts which are equal to the number of bases. So 1, 2, 3, 4, 5. And then we say, okay, let's have a Gaussian distribution here, another here, another here, another here, and another here so that it covers my data completely. Is this clear? Okay. Any other questions before we move forward? Everybody understands neural networks, right? That's the important thing, the understanding of neural networks. Theoretically, like how does it work? Why is it better than linear regression? Logistic regression, sorry, because it has more complexity. You can model more complex functions. Okay, so if there aren't any questions, let's move forward to today's lecture, which is PyTorch Basics. So we would look at some popular machine learning framework. Then we will look at some basics of PyTorch. and finally some helpers. By the way, the slides are from Mr. Chong Ru Wu. These are not my slides, but I found them very useful. They're nice slides, so I decided to use them. Okay, so there are a ton of machine learning packages. Okay, if you go back like 4 or 5 years ago, Cafe and Cafe 2 were like the most popular one. If you look at some papers that are like older paper and like were not extremely popular, you might find their code still in Cafe and Cafe 2. Any old papers which were extremely popular, their codes have been reproduced in PyTorch and TensorFlow. So TensorFlow, I think, was initially the more popular of the two algorithms. I think it started a bit early, 2015, and people started using TensorFlow quite a lot. PyTorch came in a bit late, like I think 2016, 2017. The main difference between, in terms of like where an application would be more appropriate, is TensorFlow, I think, is more appropriate for final packaging of the product. If you want to get an optimized version of the code to run on the GPUs, probably TensorFlow is a better option. But for research, for academic research, and where you want to like write code quickly and implement them and test them, I think PyTorch is the easier one. It's much more easy to write and handle. It's just like a simple Python code. So you need a bit of object-oriented programming and some knowledge of NumPy, and that's it. You can use PyTorch. Okay. So the first question that I want to ask you guys is, okay, we implemented machine learning algorithms in NumPy. Everything was fine. We can implement neural network. It didn't look like it was a huge amount of code. Why do we actually need these deep learning frameworks? Why look for something else? Why not just build them on top of NumPy? Anybody wants to make a guess for that? Okay, I'll leave this question with you. Let's think about it while I explain how popular deep learning frameworks work. So deep learning frameworks would have two types of code models. One is imperative. Imperative is just like writing some NumPy code, all the codes that we have done, where we say that, okay, A has this value, B has this value, C is a relation between A and B defined by this, D is a relation between C and a constant defined like this. All the codes that we have done are imperative. You can also have a symbolic model where you create containers, and these containers can have any value at test time. So basically this code where you define a variable A, a variable B, and then C, which is a relation between A and B, and then D, this creates like a container F, and F can have any values at test time, and it would pass them through this graph. I think TensorFlow 1 was primarily based on these type of models. I never actually have used this type of codes for my research, and I'm not like an expert in these. Generally, we use this imperative type of codes, which work very well in PyTorch, and actually are enough, I think, for any normal academic research. Okay, but just for completeness, there is also this symbolic type of code. We would not look into it in this course. I don't think you would probably need to look into it even for your academic research, but just for completeness, let's keep this here as well. Okay. So this is some history of which methods were created on top of which methods. So PyTorch was created by Torch, which was, I think, originally created on top of Lua. TensorFlow used Theano backend. It has another backend as well. I forgot the name of that. But all these methods, they were built on top of some other libraries before they eventually reached us in their final form. But basically, these two are the main libraries that people use these days. And next is also used, but I don't think it's that. Also, this is used, but it's not that common. These two are the main ones. Okay, so I'm going to leave this a little bit of introduction of other codes. This shows TensorFlow, by the way. you would simultaneously with TensorFlow, you would also hear the name of Keras. So Keras is a wrapper for TensorFlow, which makes using TensorFlow quite easy. And now Keras comes as a built-in package inside TensorFlow. When you install TensorFlow in your machine, Keras will also be installed. And you can use the Keras functionality. But again, it's just to give you guys an idea of what things are. We probably won't use it. So this is how a typical PyTorch code would look like. Okay, you want to create a network. You just create a class which inherits some properties which inherits something from nn.module. nn.module is a module inside PyTorch where we have these tools used for neural networks and convolutional neural networks defined. So for example, this nn.linear, which is a linear layer of a neural network. So let me just draw it. So this is. So this is a layer of a neural network. This is called a linear layer. This is defined inside this NN linear. So you just give it an input size and the number of hidden unit size, and it would create this layer for you. Okay. Similarly, we had this activation function, ReLU or sigmoid. These are also defined inside this torch.nn, and you can use them. Okay, we will look into this in detail, but that's basically, this part is the entire neural network. You would have to write just this code. This is like 10 lines of code, and that would define a complete neural network for you. You don't need to write any backpropagation equation. It would calculate all the backpropagation, everything for you. It's very neat. We would write this code, but just to give you guys a motivation that why people are like using these packages, because they are incredibly easy to use. Okay, so I'll come back to my question. Why do something else? Why not just use NumPy? Okay, we could write a code for a neural network in NumPy. It works fine. Why not just stick to NumPy? What's the use for PyTorch and TensorFlow? Does somebody want to make a guess about it? Notice that these packages like PyTorch, in terms of handling of the data element in imperative form, it's very similar to PyTorch. NumPy. It's very similar to NumPy. It does exactly, the data handling is exactly like NumPy. As in the tensors are exactly like NumPy arrays. But why do we need this? Why not just use NumPy? Maybe they implement some C libraries. Okay, that's close to the right answer. The thing is, they are much more efficient in solving the problems of machine learning and deep learning. Why are they more efficient? Because they can run the same codes on GPU. So if you, let's say, the neural network that we implemented with NumPy, it runs everything on a CPU, okay, which is small, which takes a longer time to run. Okay, we can do the same operation on a GPU where the problem can run much faster, and that's actually the relation. So if you run the code on Intel processor, you see that it takes what is it, 18,000 millisecond. But if you run it on a GPU, it takes like literally very small amount of time. So you get 76 times speed up. That's why these libraries were created. So you would see a lot of memes on the internet where you would see like a skeleton sitting in front of a computer, and the caption would say that, oh, I trained my neural network on CPU, and now I have to like wait forever. It didn't train. And that's actually true. If you train any large neural network on CPU, it would take an eternity to train, but you can train them much more faster on GPUs. So these deep learning packages allow you the functionality of training things on GPU. GPUs are faster. I do not know a very good answer to that, but I think probably the way GPUs handle data is that they handle 2D arrays or arrays. So if you, for example, have to do a matrix multiplication, if you do it on CPU, so let's say these are two matrices and you have to do a matrix multiplication. I think CPU would do it in some sort of sequential way. Okay, it would go to each row and multiply it with each element of a column and then add them and get a value of the output. It would be like sequential. But if you do it with GPU, they do things in parallel. So because things are in parallel, things are much more faster. In terms of arrays operation, PyTorch is faster than NumPy. Yes, in terms of array operations on array, PyTorch is much faster because PyTorch can leverage GPUs. It might be interesting just to do a simple matrix multiplication without it being on GPU and see what's the difference. We can try. But GPUs, I think, because they handle arrays, they can do these operations in parallel rather than doing it in sequential way. So remember, we saw this problem like you don't want to write for loops in NumPy. You want to do things in parallel. So it's the same thing, but for matrix product. I will actually have a look and try to come up with a better answer tomorrow. But generally, we as practitioner of the field, we just assume it as a fact that GPU can handle 2D data better or high dimensional data better, and the operations between the high dimensional are done in a more efficient way, and that's why they're much faster. But remind me this question tomorrow, Al-George, and we will have a look at it again. Okay, so again, the same performance. So it says that if you have these CUDA deep learning libraries, some of them are faster than others. So for example, these two are, both are done on a GPU, but we can see that some GPUs, if they do not have CUDA NN libraries, they are a bit slower. If they have CUDA NN libraries, they are much faster. So you can have optimized CUDA libraries for your machine learning algorithms, and that would make things faster as well. So let's look at PyTorch. So PyTorch has 3 levels of abstraction. So abstraction, as you can think of as the way of writing codes or the way of writing your functions or the way of writing your modules. So the simplest one is TensorFlow. So TensorFlow, just think of it as NumPy code. Okay, it's just NumPy code, but with the added functionality that you can run it on GPU. Okay. Then you have a variable level of abstraction, which creates these graphs. So it's basically like pipelines, and whenever you feed data into it, it goes through this entire pipeline. In PyTorch, you have the advantage of gradient being automatically computed on this pipeline. So once you define a pipeline, let's say you define this graph. So let's say this is A and B, and let's say C is A plus B, and let's say then D is C square. This is your graph. So once you feed a data into it, data would go through it. You will get C, you will get D. You will also get the gradients of the functions with respect to the variable. So you will get the gradient of C with respect to A, the gradient of C with respect to B, the gradient of D with respect to C. This is called autograd. So it calculates the gradients automatically. Okay. This is actually leveraged when we create these neural networks. So NN.module is a high-level abstraction where you have neural network layers, and convolutional neural networks are already written for us inside this module, and we just use them when we create our own neural networks. And it makes use of this autograd feature. So once you write the network, it will automatically find, once you do a forward pass, it will automatically find the gradients for you as well. Okay, so let's look at the simple level of abstraction, tensors. So you can, just like I said, it's exactly like NumPy arrays. So you can specify a data type for your tensors. You create some number of data points, number of input units, number of hidden units, number of output units, and then you just create a data X and output Y, uh, waits for the first layer, waits for the second layer. And you can actually do, this is exactly what we do. This is a forward pass of a neural network. Okay, so this is, you calculate the output of the first layer where you take X through the first hidden layer. So let me just draw it. Probably it would be a bit better. So they call it X, they call it W1, they call it W2. Okay, so, and there is a ReLU here, I think, and what is the output? Output is also through ReLU. Okay. So this, they call it H. Okay. Then they call it H underscore ReLU. Then they call this thing Y underscore thread. It's exactly like our NumPy code, by the way. But they have like this which is matrix multiplication. Okay, we had this at the rate operation. Okay, and there is a major difference in the way PyTorch handles data. I will explain it to you. Then you take the matrix product of the second and take it. Really, you can do ReLU in two ways. You can clamp at value 0. So clamping at value 0 would remove anything which is under 0, and it would just give you this, which is exactly like a ReLU. Or you can use what is the other thing that they've used? Oh, they don't have a ReLU here. This is just a simple output here. My head. Yeah. Or you would see that we have these ReLU defined, ReLU function defined inside torch.nn library. But this is just like a sample code that anything that you can do with NumPy, you can do it with PyTorch tensors as well. There are slight differences of syntax. For example, in NumPy, we use X's when we do sums and these kind of things. I think in PyTorch, you would see that they call it dimension, DIM. And similarly, this .mm, I don't think it's defined in NumPy. We have at the rate operation, but here you have .mm. So this is minor differences, which is quite easily people can get used to it. But other than that, just think of it as NumPy with the added thing that you can do it on GPU. Okay. So you see, this is the difference. So this is, if you use PyTorch with GPU, you can see that it takes 0.1 millisecond. If you do it in NumPy, it takes 350 milliseconds. So like Nawaf has pointed out, indeed, PyTorch is faster on arrays. You can do things much faster. So try to implement this code. Do this code and see what happens. Write it in Google Colab and see what happens. Okay. So, okay, we said that we use these packages because they can do things on GPU. The question is, how do we do things on GPU? How would we transfer everything to GPU? We know how to write a code, how to use the same code in GPU. Very simple. Just transfer all the data to the GPU. If the data is on the GPU, the operations would be done on the GPU. And it's very simple. You can do something like this. So when you define your data, just give it a data point of a variable on CUDA. So torch.cuda.float tensor mean that it's a float tensor which lives on GPU. Okay, so it's the same code. The only difference is that here the float tensor lives on CPU, here the float tensor lives on GPU. It might be nice to write both of these codes and say, what difference does it make? How much speed difference? I'm expecting at least of the order of 10 power, around 10 power 2 difference in terms of time. Okay, so a little bit of explanation. Here you are creating random tensors. Here you are doing the forward pass. You're creating the loss. Here you are creating, doing the backward pass. And here you are updating the gradients. I won't go into too much detail because we have already looked into it in a lot of detail. The slides would be up on the website. You can look at them. in more detail. By the way, if there are any questions, please feel free to ask them. So we are not going to look into too much detail about the variable level abstraction, because it's frankly not related to us. We won't be using it. I don't think you need to use it in any academic research, but if somebody is interested, they can go through these slides. Again, like I said, they generally define like a computational graph. And once you do the forward pass of this graph, you can use features like autograd, which would calculate the gradients automatically for you. Okay, this is actually of most interest to us, the module level abstraction, because that's how we define our neural networks. How do we specify if it's a regression or a classification problem? Well, it depends on your loss function and your data. Okay, for example, if your data is a regression-based data, y is continuous, then you would write your loss function as something like square norm loss. If, for example, your loss function, if your data is a classification type data, then you would use a binary cross entropy type loss, and the network would automatically train everything accordingly. And we would have a look at some of the examples. Particularly in PyTorch, you can see that all these packages are very readily available, and you can construct things as you feel fit. Generally, most of the deep learning applications, at least that I have worked on, generally work on classification type problems. So I don't know of any, for example, NLP, computer vision, mostly the type of problems that we deal with are classification type of problems. There must be some regression type problems, but at least I'm not aware of any from the top of my head right now. Do we need to write all the layers by hand? We will see. Just hold the question for a bit. Let's see. Okay. So let's see what is inside torch.nn. So torch.nn has all these layers: conv1, conv2, conv transpose, and things like that. These are actually convolutional layer in 1D, convolutional layer in 2D, convolutional layer in 3D, and convolutional transpose, I think, are something like inverse of like upsampling layer type of things. I'm not exactly sure what they do. Then you have pooling layer. We would see what these pooling layers do. And then you have all the loss functions, all types of loss functions. Okay, all these are done. They are implemented. You just use them. And let's see how we use them. So let's create a convolutional neural network. Actually, they have written a convolutional neural network. I would write a code for a neural network right next to it, because we would be working on a neural network. So let's say we want to do this. We have an input X. We have a first linear layer W1. We want to pass it through a ReLU. Then we have another layer W2, and we pass it through a sigmoid, and it gives us the output. Let's write a neural network for it. So what you need to do is, typically in practice, what people do is they define a class of networks which has similar architecture to what you specify. Okay, so I'll say something like, I'm defining a class of networks which inherits from nn.module. Remember, nn.module has all these layers. Everything is written inside it. You can use it. So the first thing that you need to do in a class is define the init class, the constructor. Okay, the first argument of init is self. Okay, first thing I do is I define self.linear1, the first linear layer, and it is just nn.linear. Number of input units. Let's say my data is, let's say, 10 dimensional. I want the hidden units to be 100. You don't need to hard code them, by the way. You can get them as input here. Okay, you can say that, okay, this is number of input, number of hidden, number of output. It's input to this constructor, and then you can write it ni and h. You need to define the second linear layer, self.n2, and n.linear, let's say nh and then out. Don't worry about it too much. We're going to implement it. It's just to give you guys an idea of like how to actually do it. Okay. And then we need to write a forward pass for your neural network. And forward pass would take in, of course, the object and the data, x. And then you can just say that x is self dot L1, input pass through the first linear layer. Then you do some, I'm going to write the rest of the code here. Okay. After this, you can pass x through a ReLU layer. So you can say x is equal to torch dot ReLU x. You passed the, in fact, let me just not use just x variable. You can use the same variable, convolution kernel. Yes, convolutions, let's not talk about it today. We will talk about it tomorrow. I will explain what CNNs do, but today let's wait for a little because everyone, what would be a nonlinear layer? I don't think there is a nonlinear layer, by the way. I think it's a name because it's a linear layer. It does a linear multiplication or a linear transformation. That's why it's called a linear layer. Okay, so let's call this H1 and let's call this H1 ReLU. Then you can say that H2 would be self dot linear H1 ReLU, and H2 ReLU would be torch dot ReLU or sigmoid, whichever one you want to use, H2. And then you just return it. And that's it. That's all the code you have to write. Yeah, seems like quite amazing, right? It does all the gradient calculation at the back end. You can write optimizers which would take care of the optimization. We would do it. But this is basically what we need to do. So I'm going to stop here. It does explain all the optimizers and everything, but I'm going to explain it to you in code. And I would recommend that everybody go through it because all the things that it's defining here, I'll define it in a code. Okay, let me see if I can just find a full code somewhere. Okay, this guy doing it with sequential. So now probably it's better to do it in code. So I'll do it in code and then we will answer all the questions that we have. So for the last 3 days, I don't expect you guys to do any homework. Just work on the project and try to understand these tools. So there aren't any homeworks for these days. Spend some time on your project and get used to these exercises so that you can use them. Okay, let's share my screen. This might be the right one. Okay, let's see what data I have. So I'm going to copy the code, put them in a clean line of code somewhere so that we can easily implement everything. Okay, so let me run it. Everyone, by the way, can see my screen, right? Perfect. Let me comment this out. But now this is okay, so this is how my data looks. Now let's try to use PyTorch to create a neural network in this, by the way, was a tough problem. At least I couldn't write a neural network with my hand, like 2-3 layer neural network, which can solve it. which can solve this checkerboard pattern. But let's try to solve it with a neural network which is written in PyTorch, and hopefully we would be able to find a solution for it. So the first thing that you need to import is Torch. Torch is the library, PyTorch main library. It contains everything. Then we do torch.nn as n, and this is convention. Usually people import these libraries with with these type of names, but of course you can name it anything. You can say torch.nn is, let's say, a cat, and then everything which is inside torch.nn would be inside the label cat. We need to import this code. If you run it, then it would give me autocomplete into torch.optin. So torch.optin has the optimizers. Optimizers basically are the packages which optimize your function, which do this gradient descent and stochastic gradient descent for you. Okay, so we use it to do these optimization steps for us. By the way, we will be going through code. Of course, there will be some questions. Please feel free to ask them. You can even unmute yourself and ask a question if it's too long to type in the chat. Okay. Then we do torch functional f. So we have all these functions and loss functions as classes. We also have them as functions. If you want to use the function version of this, you can use the torch.functional. If you use the class version of it, you can just use them directly from torch.nn. Okay, let me run this code. Okay, everything seems fine. Now let's create a network. So like I said, you have to define a class of network. Let's call it net. Remember camel case notation for class names. And it takes it inherits from nn.module. What is the first function that we define inside the class? It's init. Init, it's called a constructor. It's basically the interface between your class and the object of a class that you would create. Okay, let's call ni, nh, and nout. It takes ni is the number of input, nh is the number of hidden units, and out is the number of output. So let's create the layers. So I'll call it self.linear1 is equal to nn.linear ni nh. The input, one important thing to note is that PyTorch handles the data slightly differently than we handled in our neural network. So basically, I probably have to share my iPad screen for this. So what did we used to do when we defined the neural network? We did this. We said that we have an input X. It goes through the first layer, then it goes through nonlinearity, then it goes through a second layer, and so on, right? This is how we defined our neural network. PyTorch handles the data in a slightly different way. So because we draw our graphs or the flow of our data like this, let's say ReLU, W2, and sigmoid. So, and X input goes from here toward the output. The way PyTorch handles things is like this. So it's X times W1, sigmoid of this whole time, things times W2, sigmoid of it, and so on. Okay, so there is slight difference of convention. So you would see that, for example, when I was defining my input W1, its size was NH and I. But when we define it in PyTorch, it's Ni NH, because it's a transpose of the matrix multiplication. So PyTorch basically is doing this. It's saying that x times W1, ReLU of this, then times W2, ReLU of this, and so on. Does everybody understand this difference? I think the convention probably comes from the figure, because the graph data flows like this. So it's just a minor difference. There are certain advantage to it as well. The advantage is that because x is like this, the shape of x is n times the number of ni. So the first component then is the data size, the size of the data. Okay, and we would see that we would use the same convention. Okay. So let me come back to my. So you can see I'm calling it Ni times Nh. Let's define linear layer 2, which is Nn dot linear Nh times N out. And that's pretty much it. That's all that we need to do, right? Now let's define a forward pass. What would be the first argument of the forward pass? It's a method of a class. So what would be the first argument? Self, exactly. It would take the object itself, and then it would take the data, x. And let's pass the data through the first linear layer. Okay. Then let's pass it through ReLU. Then let's pass it through the second linear layer. And let's pass it through sigmoid, because we want output to be a probability. And let's return it. That's it. That should create a neural network for you. Okay. Now let me do this. Remember the data that I had defined in previous classes. It had the number of data points along, the data was along the columns, but now we want to do it along the rows. So that's why I do, when I convert it into, by the way, whenever you have something in NumPy, you want to convert it into tensor, you can just use torch.from NumPy, give it the data and give it the data type that you want. Okay, so this code just converts the data into PyTorch. In fact, let me just comment it and write it so that we do the steps together. Okay, let's write it here. So first, let's look at x and y. So what is x dot shape and y dot shape? So x is 2 times 1000, 1 time 1000. We want to get a transpose of it and convert it into tensor. So I'll call it x underscore tensor. We use torch.from underscore numpy. You can give it any numpy data, and it would convert it into a torch tensor. And then we want, what's the syntax? As type or type? Yeah, type. And we want its type to be torch.float. Okay. Similarly, we want to do it for y. So let's say torch.from underscore numpy y transpose dot type. So hopefully this works. Okay, so now we have the data in tensor form. Let's look at its shape. This is exactly what we want. The first component is the number of data points. The second component is the number of inputs. Now let's see if we can actually pass it through the network and get an output. So let's say y hat is equal to, let's create an object of this class, network class. So I'll call it net is equal to network. And what does it take? It takes, of course, the object itself. It takes the number of input unit, the number of hidden unit, and the number of output unit. So I'll create these, and I is equal to x underscore tensor dot shape 1, because we are interested in the number of columns of x. Number of hidden unit is a design choice. Number of hidden unit is a design choice. So let's say I'll take something like 10. And then number of output is equal to y underscore tensor dot shape, and it's equal to the number of columns of y. So this. Okay. So let's pass it through the network. Ni, nh, n out. So now we will have a network here. We'll have an object. Okay, let's see what's the problem. Okay. One of the things that we missed, because we have used inheritance, we have to initialize the parents as well, right? The parents of this class net. So that's why we use super. So we have to use super. So we have to initialize super, and it goes like this: net self dot underscore init. Should be fine now, hopefully. Okay, everything is fine. By the way, super also works like this. You can just give it this. This would also work. Okay, so I think this is probably a little easier to use in notation. So we will stick with it. Now let's try to give our data to the network and try to see if we can indeed get an output. So y hat is equal to net x, and let's just print y hat. Okay, this is x underscore tensor. Okay, there is a few spelling mistakes. This is linear. Here is the error. Net object has no attribute linear. Did I run it? Okay, I have to run this again because I have to reinitialize. Okay, so it seems fine, right? It's giving me a y hat. Up till now, things are fine. We created a network, we passed an input through the network, and we got an output. Everyone clear so far? Everyone agrees with what I have done? Okay. Any questions for anyone? Okay, perfect. So now let's do the optimization. Let's optimize this network. So what do we need for that? We need to first define a learning rate. Let's call it 0.001. Now, all this calculation of the gradients and writing the equations for them and then taking a step in the gradient descent, everything is done by the optimizer package inside TOS. So let's use that. So I'll create an optimizer and I'll use stochastic gradient descent optimizer. What do you give it? You give it the parameters on which you want to do the gradient descent. So which parameters do I want to do the gradient descent on? I want to do it on all parameters of my net. So this is, you just give it net dot parameters. Okay. Then I want to give it a learning rate. Learning rate is LR. You can give it other parameters as well, like decay, etc., weight decay, but I'm not going to give it that. I'm just going to give it these two. So I've defined a stochastic gradient descent algorithm, which would take all the parameters of my network, do stochastic gradient descent on that with this learning rate, 0.00. Okay. You can give it directly here as well. You can just say 0.00. That would also work. But it's good to define it as a variable like this. What else? Then let's run it for a certain number of iterations. So for I in range, let's say 1000, what do we do first? We have to do the forward pass. So y hat is equal to net x. This gives us the forward pass. We need to do another thing. We need to create a loss function. So loss function, I use nn dot binary cross entropy loss. That's it. Your loss is defined. You don't need to do anything. We just created an object of this class. Okay. So after that, you find your loss. So loss is equal to loss underscore function. I have to make sure that I use the right notation, y underscore tensor and y hat. Hopefully this will be correct. I'll give it a double check. After that, you need to write a few lines of codes, which is the first thing you need to do is you need to do optimizer zero grad. So what this line does, the optimizer has these buffers where it stores the value of the gradients. So before you create the gradients, you want to remove any old values in this buffer. So this optimizer.zero grad clears the buffer so that it can store the value of the gradients that you would calculate. Does it make sense? Optimizer, by the way, is this like stochastic gradient descent optimizer that we created here. We want it to store the values of the gradients, take a step in the gradient direction and do everything. But before we do it, we need to clear the buffer of any old values. Because inside this buffer, so it would look something like this. So let's say this would be like optimizer, let's say might have a dictionary. I don't know the structure of it, but I just want to give you guys an intuition of what it's doing. It would be, let's say, weights of linear layer 1 plus equal to grad calculated in a certain iteration, grad of loss function with respect to W1 or something like that for some data. Okay, so since it's doing the plus equal, it's good to zero it out before you add the gradients to this buffer. Dikshu? Oh, I'm sorry, it's my native language. Is it okay? Is it clear? Why do we need the zero grad? Because we want to clear out the buffers to store the values of the grade. Okay, I think it should be fine. Then all the back propagation, everything is done by this one line of code, loss.backwards. That's it. It calculates all the gradients, everything. Just one line of code, loss.backward. Loss is this loss that you defined here. Okay. All the stochastic gradient descent, everything, this is done by a single line of code, which is optimizer.step. Okay. Do we need to call net.forward at all? Yes. This, when you call this, y hat is equal to net x would call the forward pass. Okay. Let's create this and let's do ls.append. Loss is, I think, some sort of object which creates all these parameters associated with loss. Loss.item has the exact value of your loss function. Okay, so let's plot it. And hopefully we don't have any errors. Of course, it's asking for a tensor, which is exactly what it should get. Okay, I think it's because I've given it to this in wrong position. So it's why I had y underscore tensor. Okay, surprisingly it worked. So the loss is decreasing, okay, which is good. Again, I'll just go through it. So you see all this thing is done by just like 5 lines of code. You write y hat is equal to net data, which does the forward pass. You calculate the loss. You clear the optimizer buffers. You do backward pass on the loss. You take the optimization step and you append the loss. This is just for drawing purposes. But is this clear? Is this clear like what we are doing here? It's like it's 12 lines of code. So just take a second, go through each line. And if, by the way, I never asked you guys, is this size enough? Can you guys read the text of my screen? Okay, so just take a second, go through all of these lines and just make sure that you understand what each line is doing. If not, ask me, like, ask a question. See, like, okay, I don't understand what this is doing. Okay, so I'm assuming that everyone is clear about what's happening here. Now, I have done my training. I have my data. Now, let's say if I want to plot what I have actually learned, what I've gotten. So let's do that. My labels are in y hat. Okay, so if I print y hat, it's a tensor. Okay, but if I want to do, let's say, some sort of plotting, I want to let's first see if I can do the plotting directly on a tensor. So where is the plotting function? The plotting function is this. So let's take this and let's give it y hat, but let's do transpose because it's expecting it to be a row vector. And because this is coming from a sigmoid, we say that we have to give it y8 greater than 0.5. And let's plot it. It works. Okay, so we did the training. We didn't learn anything nice. It's saying everything is class 1, which means that probably we need more complex networks. So let's do that. Let's make the network a bit more complex. Okay, so what I'm going to say is I'm going to say that, okay, let's increase the size of the network. So I'll say that this is NH times NH. Maybe I'll add 2 more layers. Okay, let's do it. Let's call it layer 3. Let's call it layer 4, and let's call it an out. So I have a question for you. Is this a valid convolutional, a valid neural network? Will this work? If I do a forward pass through this neural network, which it work, will it work? Of course, it will work. What you need is, for a neural network to be valid, you need the column of the previous layer to be equal to the rows of this current layer. So if these diagonal elements are equal, it would work. It would be a valid network. And this seems like it is a valid network. Okay, so I can just copy this line of code and 1, 2. Let's make it 4. And let's make it 2 and 3. So it should be fine, right? I'm doing the first linear layer, the second linear layer, the third linear layer, the fourth linear layer, and I'm displaying the output. And I probably need to give it some more iterations. Let's try to run it now. Okay, it seems fine. Let's increase the learning rate a bit. Let's call it maybe 0.1. Let's see what happens. This, by the way, this exercise that I'm doing where I'm adjusting things, this is a significant component of machine learning research. This is what we do. We adjust parameters, we tune them, we see, okay, let's change this, let's change this, let's see what happens. Okay, still nothing. It's not a good sign. Let's give it maybe 0.3. See what happens. Okay, let's plot it. Okay, a little bit. I'm seeing something. Okay, so let's increase the number of iterations. It will take a bit of time. It's fine. Okay, let's look at it now. Okay, so a little bit. So I'll leave the rest to you. You know what to do, right? Adjust things and adjust the number of parameters, learning rate. One thing which I want to do for you guys is it's always nice to have a learning rate scheduler. Okay, we want the learning rate to be large in the beginning and then the learning rate to be small in the later layers, right? So that can be done through learning rate scheduler. So let's import the learning rate scheduler. So I think it's scheduler. Is it here? It should be here. Scheduler. Import step. Let's see if it works. Oh, I think it's an opt-in. It's an opt-in. So it's start opt-in. Learning rate scheduler. Yes. Import step LR. Okay. And what you need to give it when you're defining it, you can define a scheduler here. Scheduler and you step LR. I think it take in the optimizer. In this case, my optimizer is this. It takes the first thing, which I think is called, I forgot what it's called, but you can give it directly. You can say that, okay, you want the learning rate to change every 10,000 iteration. And then you give it a factor gamma, which would multiply, this would multiply the learning rate with this. So let's call it 0.9. Okay, and then every time you take the optimizer step, you do the scheduler step as well. Scheduler that step. I want to see if the step is changing or not. So I'll do something like this. If I mod 10,000 is equal to 0, let's print scheduler.lr. Let's hope that it works. I haven't ran it before, so let's not give it, let's give it 1,000 and let's give it 5,000. This is just for testing the scheduler part. So let's see what happens. Okay, step LR is not defined. It's not defined. Why is it not defined? Okay. Okay. What? How do we output this? So let's do this. Okay, that has this function print LR. Let's do, maybe that can print it directly. Okay. And let's run it. Okay, this is to be 1,000. Okay, what's going on? So if I is in range of this, you have to maybe returns the value. Let's print this. Okay. So let's see. I'm looking for get LR. Is there a get LR method? Yes, there is a get LR method. So let's do it here. And schedule get LR. Oh, I'm sorry, it's this. Okay, so I think that probably works. But I'm expecting it to change. So let's do print LR. And probably that was a mistake I was doing. Print LR is missing 3 required optional. I have done it in my code somewhere. Let me just see what I did. Okay, I'm using this. So I'm printing it from Param. So I'm just going to copy this. I'm printing it from inside the optimizer. So let's put it here. Okay, what have I given it to this? I've said scheduler every 1,000 iteration, get a delta of 0.9, optimize it. It should work, right? It should decrease the this, multiply it with 0.9 every iteration, but it's not doing it. Let me just double check that I've used the code correctly. Okay, so scheduler just takes an optimizer, a step size, and a gamma, and then you do scheduler.step after the optimizer.step, and that should do it. So let's see why we are not getting this here. Making stupid mistakes. Okay, so you can see that it's decaying the learning rate, which is nice. Okay, 0.3, 0.27. So I'll share this code with you. What you guys need to do is adjust the number of iterations, adjust the learning rate, and adjust the scheduler so that you can get like perfect classification. We can see that it's working. As we increase the number of iterations, things are getting better, but we want it to be like much better. So this loss, let's get it down to like 0.2 or zero point 0.1 or something like that. Okay. That's actually just play around with this code. It's not a homework. It's just to get a feel of this code. You have around 30 minutes. At we'll take a break from 11 to 11:30. At 11:30, I will resume the class and we would do like a good application of this, which is MNIST classification. We would use neural network to classify images of numbers from 0 to 9. Can you run it on GPU? Yeah, of course. That's a good suggestion. Let's run it on GPU. Let's run it on GPU. So what do we need to do? First thing I need to do is I need to take my network. So let's create a variable device, which is torch dot device, and we give it through the 0. It's identifying a device that you want to run your code on, and then you just take your network to device. You take your data to device. You take your labels to, to device. And that's it. It would run on GPU now. Okay. What you do is you would define a device. You can give it CPU as well. If you give it CPU here, it would run on CPU. If you give it a CUDA device, it would run on GPU. So what you do is you take your network to the GPU, you take your data to the GPU, you take your labels to the GPU, and then automatically the code would run on GPU. Okay. Let's say no CUDA GPUs are available. Okay, so one of the things that I should have said in the beginning is how to actually get a GPU for your Google Colab. So you come to Edit, you come to Notebook Settings, you get a hardware accelerated GPU, and you save it. Now Google Colab will assign you a GPU. Okay, so now let's run the codes. Okay, so now the code is running on GPU. Okay. Quite simple, nothing too fancy, just a simple taking everything to a GPU. Okay. Why tensor is not defined? Yes, it's not defined because I spelled it incorrectly. And hopefully this should run faster than running the code on CPU. So now this is running on GPU. So now today we learned how to create neural networks in PyTorch, how to create an optimizer, how to train the neural network, how to do a learning rate scheduler, and how to run everything on a GPU. And it is the magic of PyTorch is that it's very simple. It's like 20 lines of codes. If you clean everything up, it would be like 20 lines of code. So practice with it. I'm going to share this code immediately on the website. Just give me like 5 minutes. Practice this code. Just get a feel of everything. If there are any questions, just please note them down or ask them in the chat. I would suggest if we ask the questions at 11:30 so that everyone can contribute. So I'm expecting at least like 20 questions in total. Just note your questions. Any question is fine. When we resume at 11:30, we will go through all these questions, try to answer all your confusions, and then we will do a practical example of classifying digits, handwritten digits. You'll give me a handwritten digit, and the code will classify it for you, whether it's a 0, 1, 2, 3, something like a check reader. Okay? Is it clear? I'm looking at the chat for some yeses. Perfect. Excellent. Excellent. Let me stop sharing my screen and upload this on the website. Just after 5 minutes, you will find this notebook on the website. Thank you. Okay, guys, welcome back. Is everyone here in the meeting? Just put a simple yes in the chat so that we can start. Okay. Perfect. Okay. I think we're missing some people. There are only a few yeses. Okay. Okay, so we will start. So remember in the earlier lectures, we discussed that some of the most major successes of machine learning algorithms and deep learning algorithms are motivated by the fact that we have large data and large computation. That's the main reason for their success. So typically what would happen is that you would have your data somewhere on your hard drive. Okay. And your computation are taking place on a GPU or a CPU. Okay, and this data can be of the order of 10 to power 7 samples, 10 to power 8 samples even. This is a very large amount of data. So one of the important tools that we need when we train deep neural network is actually data handling. Okay? How do we provide this data to the GPU and CPU during training effectively and efficiently? So we've already seen that we probably don't need to give the entire data in a single go. We need to do something like a mini batch gradient descent. We need to select some random batch from this data of the order of 10 to power 1, give it here, train it, and so on. So this is done in PyTorch through a tool called data loaders. Data loaders manage the collection of data from the data set, creating batch from it, and doing it in a way such that all data is handled. So every time a random batch is sampled, it's given to the data set, you train on this, then another random batch, another random batch, another random batch, such that the entire data set is traversed, and then the data set is shuffled and this process is repeated. So data loaders is something, for me at least, programmatically speaking, this is probably, it's not, the programmatic aspect of deep learning is not challenging at all. But if something were to be classified as the challenging aspect, that probably would be the data loaders part. Writing a neural network, a deep neural network, and training it is quite simple actually. So data loaders is actually the topic for tomorrow. So we will discuss it tomorrow. I just want to give you guys this introduction just so that you know that I have a pre-written code in my code, which is doing this data loading part. We will not touch it today, but tomorrow we will write our own data loader. But today I just want you guys to understand what this bit of code is doing. It's generating data batches, mini batches to be used in training. Okay, this is the first thing. The other thing is the example that we want to solve today is actually this. We have numbers in 28 by 28 image. Let's say it's 3. We want to have a neural network which can classify, which can say whether it's 0, 1, 2, up till 9. Okay? So how would we do it? Well, we know how to construct neural networks. The input of neural network is a vector x, right? It's a vector. And then it goes into this neural network and the output is again a vector. In our case, the vector was of length 1 because we had just one class. But if you have 10 classes, it will be the vector of size 10. So the first challenge is you have this 2D data, you want to convert it into 1D data. And how can we do that? How can we convert a 2D vector into 1D vector? We did it for linear regression as well. We used a simple trick, it's nothing too fancy. But what did we do? Yeah, you can flatten it. So basically the thing is you stack it. You say that you take this image, let's say these are the columns in the image, you create a big column where you put this column here, then take this column and put it here, then take this column and put it here, and so on. So it becomes a big vector of size 28 times 28. I'm again writing it in terms of column vector, but remember, PyTorch will take it as a row vector. Okay? But since in our notation we have talked about X as a column vector, I'm sticking with the column vector representation here. Okay, and once you have that, you just can create some linear layers and train your network. So let me just write the code, how I would actually do it. So I will do something like this. You guys help me and let me know if there is any mistake. Take red color because I like it more than black. Okay, so I will do something like this. Class, let's call it again net, and it takes nn dot module. So as always, the first method would be the constructor. Constructor takes in the object itself. We would have to initialize the parents of this class. Okay. After that, we need to define linear layers. So let's create first, let's call it. I might use shorthand where I drop self somewhere, but it should be understood that self is always there. And I'm not using the right indentation, but it should be understood that then, in fact, let me just let me do the right indentation so that there is no confusion. So self dot L1 nn dot linear L is capital 28 times 28, and let's say I want 100 hidden units. Okay, self dot linear layer 2 nn dot linear 100 times 10. That's it. That's all I need in my neural network. I have two-layer neural network, which takes a 28 by 28 dimension input, take it to 100 hidden units, take the 100 hidden units, and take it to 10 output classes. Is it clear? The layers that I want to use in my network, it's clear. I want to see some more yeses, please. If there are any questions, please feel free to ask. Okay, so it seems like some people have some questions because I haven't seen that many yeses. So if there are any questions, please ask. Just say that, oh, I don't understand this. What is the structure? What's going on? And I will answer. I will try to find a way to answer it. But please feel free to ask questions. So is it clear to everyone? If there are any questions, could you ask them now? Okay, let's finish the notes. And then before I code, we will answer those questions. Then we will go to the code. Okay. So, okay, then we have to do the forward pass. So forward, and forward would take the object itself and x. Before we can do anything, we would have to convert our vector into a column vector or a row vector. In this case, it's a row vector. So for this, I can use the view option of the view method of tensors. So the view basically, you can ask a data to be viewed as a certain dimensional array. So I can say that make it -1 times 28 by 28. So 28 by 28, because it's a row vector, it should have 28 by 28 column. And -1 means that we don't care about the row, the rows. Make the rows equal to the number of data points. So it would automatically, whatever is the appropriate number here, it would put it here. So I'll give you an example. Let's say x is 3 by 3. Okay, and you ask it, you say that give me x dot view -1 times 2. Okay, no, it cannot be. Then. So let's make it 4. 3 rows, 4 columns. So this is 12. If you give it this, it would make this -1 would be 6. Because there are 12 elements, you have already fixed this. -1 would automatically be fixed to whatever is remaining. So it should be 6. But remember, you can only give 1 -1. So you cannot do this. You cannot say x dot view -1, -1, and 3. You cannot do it. You can do this 3, 2, -1. This is fine. So one dimensions can be, you can leave it blank and it would automatically be adjusted to the size of data. Is this the same as AS dot reshape? I think probably it's the same. I don't know for sure. I'm not sure whether reshape does copying of data to a different location. This, I think, does not do copying of the data to different location. So let's make a note of this as well. So I will, we need to see what is the difference between reshape and view. So I will actually have a look at this as well. And then after that, you just give it linear layer 1. Sorry. And non-linearities and so on, and that's it. You return exactly the same as we did for the simple example in 2D. Everything remains the same. Then you write the optimizer and you do the forward passing everything. So that's basically what we need to do. We will implement it in code right now. But before I do it, let's go to a clean page and let's ask the questions that you had for the previous exercise. What is momentum in the optimizer? The momentum in the optimizer is the same momentum that we discussed yesterday, the day before yesterday in optimization course, where we say that rather than taking the current, rather than taking a step in the current gradient direction, we take a weighted sum of the current gradient direction and the previous gradient directions. So this is basically, you say that, let's say the step taken at time t is alpha times the step taken at t minus 1 plus 1 minus alpha times the current gradient. So momentum is this value, alpha. Okay, so that's a good question. So basically, when you try to, when you define a variable and you use it in backpropagation, sometime when you try to do something like this, y hat, let's say greater than something or less than something, it would say that you cannot do this to a variable which is being used for which the gradient, find gradient is true. So basically think of it that y hat is part of like a graph, okay? And you cannot do anything new on this graph. So what you need to do is you need to first remove it from this backpropagation thing. So what you do is you say y hat dot detach. So what detach does is that it kind of separates y hat from your backpropagation equations, and now you can do your operations on it. Since most of the time your data would be on a GPU, you want to bring it back to CPU. So what you can do is you give it, okay, bring my data back to CPU. And then if you want to do some operations in NumPy on it, you can just simply say, and bring it back to NumPy. So now this would give you a NumPy array on the CPU. And then you can do any operation on it that you can do on a NumPy array. Does it make sense? Okay. Okay. When we are satisfied with the result of the optimization, can we somehow store the train model? Yes. For further use. So there should be net dot save. You give it path, so it should be like path dot pth or pt. Just look at the documentation of net dot save from PyTorch, or is it torch.save? Um, we will have a look at it, but there you can explicitly store and load your data sets. You don't need to retrain them every time. Any other questions for anyone? So these are 3 questions. We decided that we should have at least 20 questions, so I need another 17 questions. Okay, come on, guys, don't be shy. Any question is a good question. Don't worry about asking questions. Please ask them. Okay, so it seems like there are no questions. Let me just share my screen to work on some codes. So the first thing that we should do is save. So this is, by the way, the most important thing to do, looking at documentation. Okay, any coder, no matter how experienced he is, any programmer, this is what they do when they encounter a problem. They Google it, they look for the solution, and they use it. So, for example, we have a model, we have trained it. We can just use torch.save, model.state dictionary path, and then you can load it by defining a model of the same class and loading the weights from your path onto it. Okay. Instead of using device, is it enough to specify the data type of this? I think it's fine to do it, but I'm not sure whether you can specify the data type for a network. You can specify data types for variables, that's fine. But I think to transfer a network to a GPU, you would have to probably do net dot to device. Any other questions? Okay, if there are no questions, let's do the exercise. Okay. I think this is the data. So let me copy the code somewhere nice. Okay, this is the data loader. Okay, so let me get my data loaders. What this is doing is probably just imagine that this creates batches of data. Let's not look at other details, we will do it tomorrow. For now, this code that I'm writing, this is just it just creates batches of data for us to use in our training and testing. Okay, so this would download the data for us, create the loader. Okay, I'm not sure if the data, sometime this website doesn't work very well and you cannot download all the data, but let's see. Hopefully we would have all the data. So let's look at for badge in train underscore order. So I can do this. I just want to see some samples of the data. Um, 10 and 0 dot shape. So I want to print the size of, okay, so that's good. It seems like it's working. So you can see that the batch size is 10. We have 10 elements because I've specified it here. I asked it to get me a batch size of 10. Okay. So you have each batch has, so let me do this. So let's look at what is in a batch. Okay, so batch is a list. Okay, it has two elements. First element is the data. Second element is the label. Okay, so whenever I want to get the data, I can just do batch 0. Whenever I want to get the label, I can do batch 1. Okay, so let's do the first thing, which is let's create a network. Second. Okay, so let's create our network. So first we need to import our packages. We need to import torch. We need to import torch.nn. We need to import torch.opt10, and we probably might need torch.functional. Okay, so let's see if all the packages are fine. Okay, we have all the packages. I'm just going to delete the cell. Okay. So let's create our class, network class. So class net, it inherits from nn.module. The first, what is the first method of a class? I'm looking at the chat, guys. Constructor, exactly. So this has to be this. It takes in the object itself. We would hard code all the input output, so I'm not giving it to this. So we need to initialize the parents. So this will do it. Now let's define linear layers. So its size is 28 times 28. Hidden units are 10. Okay, nm dot linear 110. Okay, and that pretty much does it. That's all we need here. Then we need to do define a forward pass. It takes in the object itself and the data x. So x would be torch.value self dot linear 1 x, and x is equal to torch dot Do I need a redo? Let's put it and let's see if we don't use it. If we don't need it, I will remove it. Self.linear 2x, and then we just return x. Okay, that should do it for us. Okay, let's create an instance of this network class. Net is equal to net. So now this is created. Next, we need to write a code to do the gradient descent. So you can do something like this. For I in range 10, small number of iterations. We would see why this is the case, because we have, I think, 60,000 training samples, a huge amount of training data, so you don't need to run the too many iterations. Then we can say for batch in train loader, for every batch in the train loader, let's take the network to let's take everything to GPU. Okay. What do we need to do? We need to get the data, X and Y. So X is batch 0. And let's take it to the GPU. And Y is batch 1. And let's take it to the device. Let's get Y hat. Y hat would be net X. And let's calculate the loss. I'm going to use the functional just to show that this also works. Look at this. Do it. So function is equal to n dot cross entropy loss. I'm still not sure whether target is the first variable or the second variable. We'll try both and we'll see this. Next, we have to define an optimizer. So I can define an optimizer as optim.stochastic gradient descent. It would work on network.parameters. And the learning rate is, let's say, 0. Let's specify learning rate. 0.1 maybe, I don't know. Let's tune it a bit. What else? After that, we have to do optimizer.zero grad. Then we have to do last dot backward. Then we have to do optimizer.step. Let me do something else. Let me call, let's call it loss underscore total. Total loss for each iteration. Let's set it equal to 0. And let's say that loss underscore total loss equal to loss dot item. Okay. And then we can do loss dot append. Why am I doing it? Because we are dividing data set into batches. So each batch would have its loss. I want to add all of them up to calculate the total loss of one iteration. And at the end of this, I can probably plot it. is it? Yes. So let's run it. Let's see if we get any error. What are the errors? CUDA error. It is on. Let me make sure that, oh, so again, I did the mistake. The mistake is that I did not correct the shape of the data. So we needed something like x dot view minus 1, 28 times 28. Okay. Now hopefully it should be fine. Okay, so it's running. It will take some time because it's, like I said, 6,000 data points, running for 10 iterations. So while it's running, we will have a look at the code and see if there are any questions. Again, the same procedure. You just get the data, pass it through the GPU, and pass it through the network, forward pass, calculate the loss, zero out the optimizer gradient buffers, calculate the gradients, take the optimizer step, and that's it. Simple as this. Let's see what we learn. Let's let the code run and let's see what type of results we get. If they're good, if they're not good, etc. And then we go from there. So it will run. I think it will take another maybe a minute or so. We can do our discussions on the side just to see if there are any questions that you guys want me to tackle. What do you think is the pace of the class? Are we going too fast? Are we going too slow? Is it just about the right amount? Did we cover enough topics? Were you expecting some topics that we didn't cover? Just give me your thoughts, your general thoughts in the chat. Okay, good. What about other people? Has anyone found it a bit difficult, a bit easy, or very easy, or very difficult, didn't get anything? So just talk to me so that I can get a feeling of how it's going. Yes, so the next two days we would be primarily doing PyTorch. We won't be doing anything else. But the thing is, there isn't that much to do with PyTorch. That's it. Like now, you guys can train any network. Only thing that is left is convolutional neural network, which I want to explain to you guys, and data loader. So these are the two things that we would do tomorrow. And after that, you can train for any supervised learning problem. You should be able to handle it very easily. Write your own data loaders, write your own deep networks, and train them. So we probably did not import the library. Okay, so that seems a bit on and off. For me, it's really interesting in terms of putting coding and the basis right? Thank you, Nick. Let's see, can layer 2 network be worked correctly? It's a very shallow network, but that's what I want to show, that even shallow networks can work. Let's write a code and just quickly calculate the accuracy. And let's see how much accuracy that we are getting on test set. So let's do this. Let's say for batch in test loader. By the way, up till now, everything that we were doing, we were training on the same data and testing on the same data. But that's not the right approach to do. Technically, you should train on a separate data and test on a separate data. So you can see that I've trained on the train loader. Now I'm testing on test loader, test data set. So what I would do is say y hat is equal to net. Let me rewrite it, not complete. Okay. So x is equal to batch 0 to device and y is equal to batch 1 dot 2 device. And then y hat is output of this. Now, in order to find the class label of y hat, I have to find the maximum in the row, the maximum element in the row, right? Because each row represents a data point. So I have to do something like that. I have to call else the labels is equal to torch dot max, and the max has to be for x along dimension. Let me just double check. So let me come to my network and let's look at network. So the output network shape is 10. 10 is along the row. So I think I have to find my data entries are in rows. So I have to take the maximum along columns. So dim is equal to 1. Now I have to see whether y and l are same. So I can do, okay, so we have to define two variables. One is correct and one is total. So for total, I can just add plus equal to y dot shape 0. These are the number of data points. These are total data points. And for correct, I can do something like torch dot sum L is equal to y. So if y and L are same, if the label output by your network and the true label are same, then it's correct, right? So if this is done, then we can just print something like this. Accuracy is correct divided by total. Hopefully this should work. Let's see. Okay, saying test loader is not defined. Let me see what I call it. Oh, I call it test loader. It's funny, but let's use this. Let's call it test loader. Okay. So what should I do? Okay. So can I do something else to avoid this problem? It's a data. So let's see this. Let's create a new cell. Let's create a new cell and let's do z is equal to l is equal to y. And let's do type of z. Okay, so it's bool. We have to convert it into maybe that type and torch dot CUDA float tensor. You cannot use np.sum because these are tensors. You can detach them, convert them into NumPy, and then use it. Bool object has no attribute type. I thought, oh, it's, okay, I got it. I got it. So I can do this. I can say stop tensor. Hopefully that should solve it. Return of the sequence for Boolean. Let's print the. Oh, we have to do element-wise comparison. And it's just comparing the overall array. Let me see what I do to check element-wise on. I should have the code somewhere. So what am I doing? Oh, I'm sorry. I'm sorry. So I have to get the indices of the max, not the value of the max. So that was the issue, I think. So max return the value of the maximum and the index of the maximum. So we are interested in the index. And this. The size of tensor A is 28. Does not match, that's B. Okay. So let's do this. Y is a 28. So let's print y dot shape. Okay, and let's print L dot shape. Okay, it's 10, 28, 28. Why would that be? Oh, come on, I'm making a mistake. Why am I doing X? It's Y hat. I have to look at the maximum of the output. Okay, so the accuracy is 0.1, which is very low, which means that something hasn't been done correctly. Let's see, probably the learning rate is too low. Let's see what type of learning rates am I giving in my code that I've already run. I think it's probably slightly larger. So I'm giving it 0.01. Let's do that. Let's train it again. And let's see if we get something better. One zero one. Okay. 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 So it will take some time to run again. The good thing is that our codes are ready now. We should be able to see things quite clearly. While it's doing that, you guys are free to ask questions, please. Did you guys realize what mistakes I was doing here? I was doing two mistakes. One, I was finding the max of X, which I don't need. I need the max of the output labels, the probability given to output labels. So I had to change it to I had. And second, I'm not interested in the maximum value. I'm interested in the index of the maximum value so that I know which channel corresponding to which number is the maximum output probability. For example, if it's giving the maximum output probability to digit 3, then it means that it's digit 3. So that's what I'm doing here. What else? One of the thing which you guys might find a bit. Can you explain how the test data is structured? It's exactly the same. It's exactly like the train data, divided into batches, small batches of size 10. Let me just double check one thing, whether I do this. I think probably I don't need the ReLU for the second. think it only is, I have done it here as well. Probably I don't need it, but we will remove it and we'll see if it improve the result or not. Can you explain? So what are the channels? Oh, I got it. I got it. Okay. So where is the shape of the data? Okay. So this basically is how the data would look. Whenever you use a PyTorch data loader, the first element is the number of samples. Okay. Let's say in this case, I'm taking 10 samples in each batch. The second element is the number of channels in the image. Okay, if you are working with images, of course. In this case, it's a grayscale image, so you just have one channel. And the third and fourth are the rows and columns. So it's the image. Okay, so typically we see that images are number of rows times numbers of columns times number of channels. In PyTorch data loaders, you would see that it's number of channels times number of rows times number of columns. So the channel index is not the last index, it's the first index. Does it make sense? Here, so we have 10 elements are labels for digits. Yes, of course. So this label is just 10 elements, which is label for each of samples. So the first sample, the second sample, the third sample. So you have image, and then you have a label for that image. Let's say this image is digit 3. This image is digit 4. So this label, you would see that I'll print it. It would be like 0, 1, 2, 3 numbers. Does it make sense? Is it clear? If it's not, please say it's not. Can you explain again? I didn't get this, and we will have a look at it again. In fact, when the code finishes, I will kind of, it would be useful to print. I will actually, we will plot it. We will plot a data loader and a test loader. Let the code run. Has it already run? Finished running? It seems like it has. So, okay, I'm doing some mistake, but let me just first show you the data, how the data looks. So we will say for batch in frame loader, or for that matter, we can do test loader as well. Let's enumerate it, but I can batch enumerate. Then do this. Okay. So let's do this. plt.subplot, 2 rows, 5 columns, and okay. For j in range batch 0, I want to plot the entire batch and have a look at it. So let's do that. Check 0. So the number of elements are along here. So I need plt dot subplot I 2 comma 5 comma j plus 1 plt dot I have to get the image from the data, so I am is equal to batch 0 j, and then I have to, it's 1 times 28 times 28, so I have to remove the 1, so I use squeeze. Squeeze removes any index, any dimension which has size 1, and then I can do plt.im, and lt.title string the okay, label is equal to y of j. And yes, it should be, I'm sure, y is equal to batch one. Hopefully this should work. Let's see. Okay, so this is how the data, this is a batch in the data loader. You can see that label 1, label 7, label 8, label 4, etc. So you have an image and its label. That's a batch. And you can do it for multiple batches, you can plot them. So you can see that the first batch is this, the second batch is this, the third batch is this, and that's how the batches would look. You have an image and its label. Is it clear now? And this actually is a very good tool, this be able to write some visualization for your data, because you would have batches in your data exactly like this. So it's good to know some code as to visualize them effectively to see what's going on. Now let's come back to our training and see why aren't we improving? Why isn't our loss improving? Let's just make sure that everything is in order. I make the stupid mistake every time. I don't take step in optimizer direction because I didn't put the parentheses. Half of the blame is on you guys because you guys didn't point it out for me. I'll take half of the blame because I make the mistake. But half of the blame is on you guys. You guys should have caught it. Okay, so while it's running for the third time, let's see what else we can see here. Nothing too fancy, just simple. And you can do it for test loader as well. You can see some samples. Any other questions? Jaws, is it clear? Do you get how a batch looks? What does a batch have? Some numbers are mirrored. Does this have any effect on training? Yes. So basically, this is basically from our training data. That's how we have labeled our data. Yeah. So, for example, if it were up to me, I would not call it a 7. I would say this is not 7. Oh, I have to check whether I've done it in my. I might have done it in my data loader if I've given any transforms. Yeah, I have actually done it. I have asked it to horizontal flip the images. So it's me. I ask it to flip the images horizontally because I want my method to be robust to flipping of image, but I should probably not do it for MNest. But that's why you have flip. This is because of what I have done to the data. Okay. Let's hope that third time is lucky for us. Okay, finally we have something nice and the loss is decreasing. Let's look at the accuracy. And we have an 89% accuracy, which is great, right? For a very simple code, two-layer network, we can label them quite well. which is great. So if there are any questions, please ask them. Otherwise, I'm going to share this notebook with you and just play around with this code. What I want you guys to do is display the test images and their labels for, let's say, 100 samples. Okay? Labels which is output by your network, or maybe find the samples. Okay, this is your task. You will go over the data. You will find all the samples which are labeled incorrectly, and you would plot the image and the label assigned to that image by the network. Can you guys do it? I want a yes or a yes and no in the chat, please. All 25 of you have to answer, please, so that I know whether you understand the question or not. Yes, go over the training set, the test set, sorry. Go over the test data, find all the images which are labeled incorrectly, plot them, and show their incorrect label in the title. Because 10% of the data is incorrectly labeled, right? I want to see which samples are incorrectly labeled. Why are they incorrectly labeled? So in order to be able to do that, I have to go over the test data, find all the samples which are incorrectly labeled. You don't have to do anything. It would just use this code, but you have to just think smartly. How do you find the samples which are incorrectly labeled? Then plot them, and then show the incorrect label in the title. The correct label, you can also show the correct label, but we know the correct label because we can see the digit. Is it clear to everyone? So let me just write it here. So let's do this. So the task is this. This. So the task is this. The training data. Yes, training data is correct. Go over all test data. Okay. Find images where output label, output of neural network label does not match true label. True label is the ground truth. Show the images, show all such images and the incorrect label in the title. Again, when I say incorrect label, I mean the incorrect label which is output by your network. Okay, of course, the correct label would always be correct, but your network would assign it a label. Your network would say, oh, this is 3, or this is 4, or this is 5. Okay. So rather than plotting y here, you would plot y hat. Y hat is the index of y hat. Is it clear to everyone? Do you guys understand what I'm asking? Okay. 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 So that's perfect. I'm going to stop sharing my screen. I'm going to immediately upload this on the website so that you guys can actually use it. Give me just 5 minutes. Okay, guys, so I've made the changes and I've pushed them to the website. Just give it a minute or so, it would show up there. Good luck with the exercises. You have 30 minutes. It's not a homework exercise, just to give you guys a feel of how to work with this data. Don't worry about like completing it as in like while grade or anything on it. It's just enjoy the code, just enjoy the experience and try to see how it works. Okay, thank you.